Hi, everyone, and welcome to Lowell Observatory's second interactive stargazing stream. My name is Megan, and I'm an educator up on Mars Hill. Tonight, although you can't see them, we have Sarah operating the telescope at the observatory, and we also have Danielle and Heather helping us out with the stream. So thanks to them. Now, what you should be seeing now are the telescopes at the GODO, the Giovale Open Deck Observatory. And hopefully you got a little introduction to them with the really beautiful video we put together for you guys at the beginning. So I'm just going to talk briefly about the telescopes that you're seeing. Now, the one that has the red cord around it, that's the one we're going to be using tonight. That's what we call the 14-inch plane wave telescope. So it's completely operated by a computer, and there's a camera hooked up to it where the eyepiece would be. Now, next to the 14-inch, we also have a 17-inch plane wave telescope. And it's actually operated by the same computer system, but instead of a camera, we have a spectrograph on it. So a spectrograph is an instrument of spectroscopy, and it's a really interesting field of science to be in, and we are actually going to talk about it in more detail a little bit later tonight when we look at a super fun object called the Ring Nebula. But in order to see it, we'll have to wait until around 8:50. For now, let's go ahead and go straight to the moon, which is what we're viewing at the moment. So the moon, obviously, it's the brightest object in the sky besides the sun. And tonight we're able to see just about half of it. So while we have the moon up here, I'm going to talk to you guys about some of the really common phrases that we use when observing the moon. So first of all, if everybody can see this line on the moon, right where the shadow meets the brighter edge, so right about here, this is what we call the terminator line. So if you're ever at the observatory and you hear one of the educators say, look at the terminator line, it's really easy to see the craters there. It's just where that shadow is meeting the rest of the moon. So now another two very commonly used phrases when we're talking about the moon are the lunar highlands and the lunar maria. So these refer to the two types of surfaces we find on the moon. So the first one is the super dark areas, like this part right here. This is called the lunar maria, and that's Latin for sea. And that's because very early on, astronomers actually mistook these areas to be actual seas on the moon. Now, every other surface you see on the moon, so all the white spots, these are what we call the lunar highlands. And these are much older than the maria, believe it or not. Now, how do we know this? It actually has to do with the amount of craters on here. So there's more craters on the highlands, which means that they've existed for a longer amount of time and have had a lot of time for objects to hit them and create these craters. Now, since the moon doesn't really have an atmosphere, all of these features get really well preserved for millions and billions of years. Now, if you look at the maria, you'll notice that there's not nearly as many craters on it. And this alludes to us that the maria must be much younger surfaces. So now we're going to take a look at our first object, and that's going to be a little binary star called Algieba. So Algieba, super, super cute. That's in the constellation of Leo the Lion. In fact, it has a more scientific name, which is Gamma Leonis. Now, Algieba, of course, it has two stars in the system, which you can see here. Now, the brighter star there is what we call a K-type giant star, and the smaller one is a G-type star. Now, very recently, we found out that the larger star actually has a planetary companion, which is super exciting. Exoplanetary science is a very young field, but ever since we started discovering these exoplanets, we have been discovering exponentially more every year. And I'm pretty sure the total count is right around 4,500 discovered exoplanets. So the brighter star here has a planetary companion that's about 10 times the size of Jupiter, but it orbits really, really close to the star. It actually orbits at a distance from the star that's the same as the Earth's distance from the sun. So it has an Earth-like orbit, yet it is a giant gas giant planet. Because of this, it's what we call a hot Jupiter. So that would be its exoplanet classification. All right. So Algieba, just so we're all on the same page, is 103 light years away from us. So let's talk about a light year really quick, because I'm going to use that terminology a lot. So 1 light year is the distance light will travel in a year. So it's kind of confusing because it's a measure of time and it's a measure of distance, but let's try to break it down a little bit. So light travels at the same speed in space no matter what, and that is 3 times 10 to the 8th meters per second. That makes no sense to anybody, right? It's about 700 million miles per hour. Now, if you just put a light particle out in space and let it go and just keep going for as long as it wanted for a year, that distance is what we refer to as a light year. And what this means is that 1 light year means that a light particle needs an entire year to travel that distance. So if you're looking at an object 1 light year away from you, you're seeing the light that left that object 1 year ago, which means you're looking back in time at that object. So when we look at Algieba, which is 103 light years away from us, that means that we're looking 103 years into the past. Pretty cool stuff. I like to give one other example of this. And in order to do that, we're going to go to M61, which is a spiral nebula and actually has something else exciting about it. But before I get to that, let's talk about its distance. It's 60 million light years away. So imagine that you are on a planet in M61 in this spiral galaxy, and you look over at the Milky Way galaxy, 60 million light years away from you, and you see Earth. And you have a high enough powered telescope to view the Earth's surface. Well, you would be viewing the Earth as it was 60 million years ago. What was happening here 60 million years ago? Dinosaurs. So if you were in M61 and you were looking at Earth, you would see dinosaurs. So light speed and light years are pretty cool stuff. All right. So now we're able to see M61, and if we zoom in a little bit, which Sarah is doing now for us, thank you, Sarah, you should see 3 bright objects right around the disk of M61. Now we're interested in one of those bright objects, and in particular, we're interested in this guy. So what's so exciting about a white dot? Well, that is actually a supernova. So supernova just went off in M61, and I'm pretty sure we looked at this in the last interactive stargazing last week, but it's just so cool that we had to look at it again. And now this supernova just went off, but of course, M61 is 60 million light years away from us. So that means the supernova actually went off 60 million years ago. It's just pretty cool to think about. Now, what actually is a supernova? So it's one of the ways that stars can die. We have 3 main ways that stars can die. And they're actually split up by mass. So we have very low mass stars, medium mass stars, and very high mass stars. So we're going to talk about what happens to the medium stars later, like our sun. But for now, let's talk about those very, very high mass stars. What happens is, inside of their cores, they're going through this process of nuclear fusion, just like all stars. It's just that very high mass stars are a little bit better at it because they can have hotter temperatures. So what happens is they convert hydrogen to helium, and then they run out of hydrogen, and they're like, oh no, what do I do? Oh, I have all this helium that I've just created. I guess I'll start fusing that. So they get a little hotter, and they start fusing helium into carbon. And they do that for however long they can, and then they run out of helium, and they're like, oh no, what do I do? Well, now I have all this carbon. So they start taking carbon and fusing it into oxygen. And this process just keeps going on and on and on until the star's core reaches iron. And unfortunately, iron is the end of the road. You can't go past it. So as soon as a star reaches an iron core, that's the end of the line. And the star explodes in the most energetic event that we can witness in the universe. And it's so energetic that, as you can see from this picture, a supernova can actually briefly outshine the light of its entire galaxy, which is really cool. Now, what else is cool about supernovas is that is where most of the periodic table comes from. So, like I said, stars can create elements in their core all the way up till iron, but they can't do anything past iron without exploding. So in these supernovas is where all of those heavier elements come from, for the most part. So when you really think about it, this is why astronomers like to say, we are all made of star stuff, because a lot of the elements in your bodies had to come from supernovas. There was no other explanation for it. So that's very exciting and really, really cool. Now, in our own universe, or in our own galaxy, we actually have a star that's about to go supernova very soon. And by very soon, I mean maybe within the next couple hundred to couple thousand years, who knows? But this star is called Betelgeuse, and it is in the constellation of Orion, which I do believe is just about to be setting at this time of the year. It's a winter constellation. So we're not going to look at that tonight. But I just wanted to mention that it exists. So why don't we move on to our next object, which is going to be the Sombrero Galaxy. So it's M104. So you might hear me talking about M this or M that, M5, M61, M104. This all refers to the same catalog. It's the Messier catalog. And it was created by an astronomer called Charles Messier. Now, it's a pretty funny story of how he created this catalog. Essentially, Charles Messier was a comet hunter. And back at the time that he lived, this was a super lucrative profession. If you could find comets, you got a lot of money for it, for the naming rights specifically. And Charles Messier kept looking for comets, but instead he kept seeing these galaxies, and he saw these star clusters and these nebulae, and he was getting really, really frustrated that he kept finding these objects that he thought were comets and then turned out to not be comets. So in his frustration, he said, you know what? I'm just going to make a list of all the places that I've already looked that aren't comets. And it's really funny because Charles Messier's list for him was a list of annoying objects that kept getting in his way. But nowadays, it's actually the reason why he's most famous. So what we're looking at right now is M104, so that's Messier Object 104, and it's called the Sombrero Galaxy. So what's really cool about this is that we have a nice edge-on view of this galaxy. So you can see the galactic bulge here, and you can see the disk, kind of like this. And this kind of black part of the disk right here, and I'll erase everything so you can see it, that black part of the disk right there is primarily made up of dust, which is why it's blocking out the light for our eyes. If you were to look at this and say infrared, though, this part of the disk that looks black might actually be glowing to you. So pretty cool stuff there. And that's kind of getting into the whole spectroscopy idea. We'll talk about that a little bit later with the Ring Nebula. Now, the Sombrero Galaxy is also super important to all of us here at Lowell Observatory because our second director of the observatory, Vesto Slifer, actually made an incredible discovery that began with this galaxy right here. So this is a version of spectroscopy that he was using. He was looking at the Doppler shift of distant galaxies, but at the time they thought they were nebulae. So let's pause for a second. What is Doppler shift? So Doppler shift, whether you know it or not, affects your life every single day, and you probably experience it every day. If you're ever driving down the road and a car's coming towards you or a train's coming towards you and the horn is on and it sounds like it's getting higher and higher pitches of coming towards you, and then it passes you and it sounds like it gets deeper and deeper, kind of like meow, like that. That is Doppler shift for sound. Light also has Doppler shift. So if you have an object and it's moving towards you really, really fast, it's going to appear bluer than normal. Or if you have an object and it's moving away from you really, really fast, it's going to appear redder than normal. So Vesto Slifer took a look at the Sombrero Galaxy and measured its Doppler shift, and he found that it was insanely redshifted to a very large degree. So much so that he was kind of curious if he had made a mistake, because it implied that this galaxy, at the time, Nebula, was moving at unfathomable speeds away from us. Now, Vesto Slifer didn't really know what this meant, but he kept on measuring galaxies, at the time nebulae, and he found that almost all of them had these extreme red shifts, except for a couple like the Andromeda Galaxy, which had blue shifts. And now he didn't really know what this meant, once again, but he put his data out there, and it was eventually used by Edwin Hubble to determine that the universe was expanding. So pretty cool stuff. And it was used to develop his Hubble's law. So we're going to go ahead and move to the next object. Now, if anybody has any requests, feel free to put those in the comments. That would be awesome. We're happy to look at whatever you guys want to look at. So the next object that I'd like to look at, let's take a look at, how about M5, if you think we can get that, Sarah? So I have a request to see Andromeda. Unfortunately, I think that might just be a little bit too low in the sky right now. Feel free to correct me if I'm wrong, Sarah. But that is much easier to see a little bit earlier in the year or a little bit later in the year. Yeah, I just got the confirmation. It is a little too low in the sky. Sorry about that. Okay, so this next object that we just pulled up on the screen is M5. So this is a globular cluster that's about 25,000 light years away from us. So 25,000 light years away from us, that means what we're seeing is from 25,000 years ago. Now, there's two types of star clusters. We have globular star clusters and we have open star clusters. What's the difference between them? For all intents and purposes, for us here today, primarily it's their age and their location in the galaxy. So globular star clusters are much, much older than open star clusters. And they're also found much more spread out from the center of the galaxy. So they're in what we call the galaxy's halo. So we have let's talk about two different parts of the galaxy. We have the disk, which is where we live, and we have the halo, which is kind of a sphere surrounding the entire galaxy. Globular clusters tend to be in the halo. And now, what's really interesting about these globs is that they help inform us on how the galaxy was formed and what was happening at that time. And for the reason for this is because of their age, because they're actually old enough to have been created when the galaxy was also being created. Now, globular clusters are primarily made up of very low mass, very cool stars, and there's a reason for this. High mass and hot stars tend to have very, very short lifetimes. They're what we call the rock stars of the star world. So they live fast, die young. Low mass stars, cold stars like M-type stars, live for very, very long periods of time. So for globular star clusters, which are very, very old, they're actually so old that they can't really have any high mass stars because they all would have died by now. So they're primarily just made up of those itty bitty little low mass stars. Open star clusters, on the other hand, can have a mix of both. All right, so now I have a request to see Antares, which is doable for us. So why don't we go ahead and move over to it? All right, so Antares is just a little bit low on the horizon, but we're still going to be able to get it all right. So going over there right now. All right, there it is. Look at that. Super cute. Okay. So Antares is a red supergiant star. Now, there's different classes of stars. We have main sequence, giant, supergiant, white dwarf, and this is what we call the supergiant. So it's about as big gets, and most likely will go supernova one day. We talked about that a little bit with the supernova we saw in M61. So one day, Antares will probably run out of fuel to actually continue its nuclear fusion, and it will explode and create lots of different elements that maybe one day could be involved in an alien civilization. So now Sarah's going to do something for us, which is where she turns up the exposure time way up. So right here is what she's doing. So this is the amount of time that the telescope is actually taking light in. So there's two ways to make your image brighter. You can either turn up the exposure time like that, or you can turn up the gain up here. Either one will kind of do the trick. But right now what we're seeing is the star seems to have developed some new features when we make it brighter like this. You see these spikes that look like this. Those are my spikes. I hope everybody enjoys my artistry skills tonight. But anyways, those spikes, a lot of people ask me why stars shine like that. It actually doesn't have to do with the star. It has to do with the telescope. So the telescope, the geometry of the mirror actually affects the way these spikes come off of the star. And if you have different supports on the mirror, the shapes of these spikes will actually be different. So this is what we call diffraction. or this is a product of what we call diffraction. All right, so I have some good requests now. We have M63, M94, M51, and M106, so lots of requests. Since it's my choice, let's go M51 because it's like so cool, you guys. So M51 is what we call the Whirlpool Galaxy. And the Whirlpool Galaxy is in the process of something super interesting in astronomy. And it's actually one of my favorite scientific words. It's called galactic cannibalism. So it's when one galaxy absorbs another galaxy. And that is actually what it's called, by the way. I'm not even making that up. And this is a process that will actually happen to the Milky Way eventually, too. So we're kind of looking in the future with this one. All right. Okay, so it's just barely starting to come into view. If you want to turn up the exposure time a little bit, Sarah. So you're just able to start seeing some of the spiral shape here. Ooh, kind of messed that one up. Here, let me try that one more time. You're starting to see some of the spiral shape come in here. And you're able to see the centers of the two galaxies we're looking at. So here is the center of the largest galaxy, and here's the center of the little itty bitty guy that he's eating. All right. So what's going to happen to the Milky Way? Well, as we speak right now, a very large galaxy in our group called Andromeda is hurtling towards us very, very, very quickly. Settling, isn't it? And in about 10 days, just kidding, in about 5 billion years, Andromeda is going to crash into the Milky Way and it's going to eat us in a process, once again, called galactic cannibalism. And at some point, we'll probably look a lot like this. So here you can see the Whirlpool Galaxy very nicely eating the little galaxy right there. Super cool stuff. That looks great, Sarah. Thank you so much. I'll also take this opportunity to talk just a little bit about spiral galaxies. So spiral galaxies tend to have two very major arms. That's the most common thing that we see. So as for the Whirlpool Galaxy, you can see it's a very large one here, and you can see another very large one here. All right, awesome. Well, let's move on to the next object. Let's take a look at M94, because I don't think we looked at that last week. At least that's what Sarah is telling me. All right, so I don't know if you guys can see it on YouTube, but we have a little system for moving the telescope that actually shows us the entire night sky, all the constellations, and the deep space objects within them. And it makes it super easy for us to just be able to click on those objects and tell the telescope to just slew right to it. And I believe you guys are able to see the telescope slewing, so you can see that it actually moves quite quickly, which is handy for us, let me tell you. Okay, so we should be just about moved to M94 now. All right, yes, there it is. Well, in 10 seconds, there it is. So M94 is a neat little spiral galaxy in the constellation of Canis Veneci, if I can pronounce that right. Sometimes the pronunciations are lost on me, I'll be honest. Ah, there it is. Beautiful. Okay, M94. So what you're seeing in this picture, of course, the brightest object is going to be the center of the galaxy. And then around it, you're seeing those spiral arms again, just like the Whirlpool. So we're kind of seeing them come off here and here and here. But they're much more tightly wound to M94 than, say, the Whirlpool Galaxy was. And this is actually alluding to how astronomers categorize spiral galaxies. So we assign spiral galaxies A, B, C, D, E, F, and lots of those, or those letters specifically, have to do with A, the size of the center of the galaxy, so the size of this guy right here, and B, how tightly wound the arms are to that center. Pretty cool stuff. All right, so now we're going to try M44. So that's the beehive cluster. It might be too big for the telescope, but we're going to give it a shot. And then after that, we're going to take a look at the Ring Nebula because I have been waiting all night to see it. But let's give the beehive a try first. Okay, so what you're seeing right now is Sarah is adjusting the exposure time of the telescope, and the telescope is also going to be slewing while she's doing this. She's preparing it for the Beehive cluster. Okay. Well, it might be a little too big for us. We're seeing some of those brighter stars in the cluster, that's for sure. But we might as well talk about what type of cluster it is too. So this is an open star cluster. So you might remember when we looked at M5, I talked about globulars. So this is the counterpart to globulars. These are opens. Now you might notice that opens tend to be much more spread out than globulars, which are very gravitationally bound. And in addition to that, I'll reiterate that open star clusters have all types of stars in them: high mass, high energy, low mass, whereas globular clusters just have those low mass cold stars. In addition to that, open star clusters are found more of in the disk of the galaxy, just like us here on Earth. It's pretty cool. All right, and we're starting to see some of that diffraction grading again. You can kind of see the spikes from the star right there. Pretty cool. All right, well, I think we've had our fill of Beehive. Let's move over to the Ring Nebula, and we're going to talk about this for a little bit. This is a super cool object. I'm hoping that it's in a good spot so we'll be able to see it. So I got a request for the Big Dipper. Unfortunately, the Big Dipper is a constellation, so that's going to be way too big for the telescope to see. But if you want to see the Big Dipper, just go outside, take a look at the sky, and you should be able to find it no problem. But anyways, back to the Ring Nebula. So it's about to pop up on the screen here in like 4 seconds. And the Ring Nebula is the aftermath of the death of a medium-sized star. Wow, look at that. That looks awesome. Okay, everybody can see that, hopefully. I'm not even going to go ahead and circle it because I'm sure you guys know what you're looking at. But anyways, back to what I was saying. So the Ring Nebula is what we call a planetary nebula, which has literally nothing to do with planets. I'm going to reiterate this. Planetary nebulae have nothing to do with planets. It's just that way back in the day, astronomers saw them and thought, maybe they have something to do with planets. And they were wrong, but the name stuck. So we call it that anyways. But now planetary nebula are the aftermath of the deaths of medium-sized stars. So for example, when our sun dies eventually, this is most likely what it's going to become. And what happens is that star fuses material in its center, just like high mass stars, until it reaches the point where it can't fuse any more material. And instead of having this massively energetic explosion like a supernova, it just kind of puffs out its outer layers. It's very anticlimactic for a star. But for example, let's take the sun. And like 5 billion years from now, the sun's going to die. And what's going to happen is it'll blow up first to what we call a red giant star. And then when it really dies, it'll just blow off all this outer material. And what will be left is the tiny itty bitty little center of the star. And this tiny little itty bitty center that's left over is what we call the white dwarf. And you can actually see it tonight. So it's right here. It's that itty bitty little white dot in the center. Super cool. Super, super cool. Now I'm going to ask Sarah to keep it nice and zoomed in like that so that we can see those beautiful colors coming through. Now, why are objects in space colored in different ways? So this is getting back to that idea of spectroscopy that we were talking about. Different elements and different molecules have their own fingerprints of light, and these fingerprints correspond to different colors. So looking at the colors of an object like this can actually help inform us astronomers about what it's made of. So for example, in the Ring Nebula, the two noticeable colors are blue at the center, more towards the center, and that is because it has a very high abundance of helium. And now on the outer edge, we see that red, and that beautiful red is because it has a higher abundance of nitrogen there. All right, so it is about 9 o'clock now, so we're going to take just a couple more requests. So let's see, we got the Skull Nebula. Unfortunately, it doesn't look like we'll be able to view that since it's in the constellation of Cetus, which is not in a good place in the sky for us at the moment. But we can take a look at Mizar and Alcor, which are 2 stars within the Big Dipper. So Mizar and Alcor At first glance, right, you see this little, it's the middle star in the handle of the Big Dipper. So at first glance, you're like, oh, that's just a star. It's just a part of the handle. At second glance, you might notice that it's actually 2 stars. And you're like, whoa, that's super cool. There's actually 2 stars there. But then at third glance, you actually see 4. And third glance, by the way, disclaimer, third glance has to be with a telescope. But there you go. So these are all in a system together that we're seeing. So we have 2 itty bitty little stars here, and then we have 2 stars kind of out here. And these are all doing that orbital dance together. All right, super cool. So let's take a look at some other stuff. So we got a request earlier in the night for M63, and I actually really like M63. So why don't we go ahead and take a look at that? So that's called the Sunflower Galaxy. Disclaimer, I don't really think it looks like a sunflower. You can disagree with me if you'd like. Well, maybe. Well, let's take a look at it. Maybe we can get a sunflower out of it. But anyways, this is a spiral galaxy. So this is one of the more common types of galaxies, spirals. So just like the Milky Way. Now, you might notice, I don't know if you can see it at the bottom of the screen. We have the exposure countdown. So right now, for example, Sarah has it set to 15 seconds, which means for 15 seconds, the telescope holds its lens open and gathers light and gathers light and gathers light, and then gives us the image of that entire 15-second period. And then it does it again and again and again and again until we tell it to stop. So we're seeing M63 right here. There's the little center of the galaxy, teeny tiny little guy. Very cute. I guess it could be a sunflower, I suppose. Maybe on a darker night, you'd be able to see it better. Let's just take a look at the next picture that's going to come up of it. Ah, that's much better. Can we zoom in on that, Sarah? Okay, so that's interesting. It's a cute little guy. So, of course, once again, we can see the galactic center right about there. And now we're seeing all these spiral arms coming off, so you can kind of see them, even if they're really, really faint for you guys. Like that. And we're also seeing lots of dust building up right around the center. Ooh, pretty cool. All right, so let's take a look at the next request. So we're going to look at a Comet Panstarrs. We're working on getting the RA in deck for that at the moment. So before then, let's take a look at M92. All right, so we're going to take a look at M92, and then the Penguin Galaxy, and then Comet Panstarrs, and then I think we're going to call it a night after that. All right. Beautiful. So M92, let's talk about that. That is a neat little globular cluster. So we've already talked a little bit about these globs. Some of them look cooler than others. I will be the first to admit that. But I don't think I mentioned how many stars make up globular clusters. And we're looking at about 500,000 stars. That's kind of an average number for most globulars. Now, in addition to that, a big question that comes up is, why are globular clusters so much more tightly compacted than open star clusters? And globular star clusters, the reason for this is because we believe there's something in the center holding them together. Now, in some cases, and I say some as a disclaimer because we don't think that all globulars have these, but in some cases, it's medium-sized black holes that are holding them together, or very low mass black holes, solar mass black holes, if you will. So this is super interesting stuff, of course, because black holes are probably everybody's favorite thing in the world. And just for a brief overview of what a black hole actually is, it's what we call a singularity. So it's a single point in space-time, which is hard for us to imagine. But imagine a single point with infinite density and zero volume, which means that if you get too close to this point, its gravity will be so strong that you will never be able to escape it. Even light can't escape it. And that is what a black hole is. Okay, so let's take a look at the Penguin Galaxy. And then we'll take a look at the comet. It'll be super cool. So full disclosure, I actually haven't seen the Penguin Galaxy myself, so I'm really excited for this. I think a good goal is every time you go stargazing, try to view at least one object you haven't seen yet. All right. Okay. Cool. So we still have the glob up on the screen, which is probably what you all are seeing, but in about 4 seconds, the telescope will take its new picture of this galaxy. We'll all get to view it together. Oh, it's a little itty bitty thing. Okay, I'll circle it out for you guys. It's right there. Sometimes it's hard to tell galaxies apart from stars, so you gotta you gotta have a well-trained eye for it. All right, pretty cool. Okay, well, let's move on to the comet, since we're just about out of time here, right after this next exposure. So give it in 8 more seconds, we'll hopefully get a better view of this Penguin Galaxy. Oh, there she is. Okay, pretty cool. Oh, here, I'll circle it again, Sarah, don't worry. You can zoom in. All right, so hopefully now it's a little bit easier for everybody to see that it's more of a galaxy and less of a star. I know it is a little bit difficult to tell, but you can kind of see some of this gas. Oh, if you zoom back in, Sarah, for me. All right, so you can kind of see some of this gas and dust coming off the galaxy here on the edges. It's hard for me to point that out, so I apologize because it's so tiny. But pretty cool, you know? This is a learning experience for me too. So let's take a look at the comet and then call it a night. So comets are really interesting. Comets are in these very long orbital period, highly elliptical orbits around the sun. So I know that's some kind of technical terms, but highly elliptical, what does that mean? Well, you have circular orbits, right? So imagine this is a perfect circle. And the more I squish it, and the more I squish it, and the more I squish it, the more elliptical it becomes. So comets, unlike planets, have these extremely ovular elliptical orbits, whereas planets have more circular orbits. They're not perfectly circular, but they're much, much more circular than comets are. So comets are also the thing that cause meteor showers here on Earth. So what happens is lots of different dust and material, mostly ice, is coming off of the comet, off of its tail, and it kind of fills up the entire orbit of the comet. So it fills up this entire area. And whenever the Earth moves through the comet's orbital path, we get showered in this debris of material that the comet has left behind. And that is what causes meteor showers. Okay, so we have a picture up on the screen. Sarah, do you want to go ahead and zoom in on this if you see the comet? I'm not seeing it. Does not seem to be here. It's possible that we got our RA and declination, our rate ascension and declination, which is coordinates that we use in astronomy. It's possible that we got them kind of wrong. We're going to try to fix that. We'll give it one more shot. All right. So like I was saying, meteor showers are caused when the Earth moves through the orbital path of comets. So if you can think of very common meteor showers like the Perseids or the Geminids or the Orionids, you can actually go online and look up and see which comet is causing these things. It's pretty cool. All right, so we have new RA and dec coordinates. So let me talk about that a little bit. Like I said, they're called right ascension and declination. So this is the most common coordinate system we use in astronomy. And basically, it corresponds to latitude and longitude. So if you were to take the latitude and longitude lines of the Earth and project them out onto space, that would be right ascension and declination. Oh, there it is. Look at that. Okay, so here's the comet. That's awesome. Cool, cool, cool. So there it is, Panstarrs. Super, super cool. Love seeing comets. All right. Well, it's about 10 past 9, so I think we're going to wrap it up for tonight. This has been incredibly fun for me, even though I'm just kind of sitting here talking to myself. And while we wrap it up, hopefully we'll get a better picture of the comet as well. But yeah, this has been fun for me talking to myself here. And I hope you guys tune in for our next interactive stargazing next week with another new educator. And we look forward to seeing you guys on the hill. And now if I can direct your attention back to the comet real quick before I log out, we can see that it's nice and bright now. And it looks a little bit fuzzier than the surrounding stars. It also kind of has a halo of light around it, which is one of the ways that you can tell that it's a comet and not a star. Okay. With that, thank you, Sarah. Thank you, Danielle. Thank you, Heather. And thank you, Lowell. And we look forward to being able to educate you guys in person once again someday. All right, have a good night.